recording. So I was saying if you got a 68 on your test, don't freak out. Everything's going to be okay. And I was also in the middle of talking about how the chapter 2 material is in general easier than chapter 1 and easier than chapter 3 and easier than chapter 4. So if you did not do as well on chapter 1 as you had hoped, then you should hopefully do really well on the next test. Usually test 2 is where students will boost up their grade and kind of give themselves a little bit of a buffer. Also, don't forget that I will drop your lowest test score. So you have 5 exams, and I'll drop the lowest exam score. So if you totally bombed this one and you do better on the later ones, then this might be one that you drop. So don't freak out. So, oh, and I was also saying Calc 1, yes, in the summer, comes at you very, very quickly. Chapter 2 is only 5 sections. We've already done 2 of them. 2, 3, and 2, 4 are, I never want to say that anything is easy, but they're very, very, very straightforward. 2, 5 is pretty straightforward also. So 2, 3, 2, 4, 2, 5 are not going to give you a hard time. So if you were really struggling with the 2, 1, 2, 2 homework, I know I had a couple people who asked me for extensions. If you feel like, okay, I'm going to get through 2, 3, 2, 4, I'm going to kind of breeze through that, and maybe I would like to take a little bit more time on 2, 1, 2, 2, request an extension. It's fine. I mean, I want you to be prepared because officially your test is scheduled for Thursday. Like as in 3 days from now. I was even thinking like, could we scoot it to Monday? But really we can't, because we're gonna have we will have finished all the material by Wednesday, and then you'll have asynchronous work over the weekend. And the last thing I want to do is give you asynchronous work in another chapter that you're not even gonna look at because you're gonna be too busy studying for an exam that Monday. So as much as I'm not thrilled with having a Thursday test and such a quick turnaround, it is going to be easier material for this test. This tends to be students' best test in the class, and it kind of just makes sense that that's where it goes. That's where it was on the tentative schedule. So that's where I'm planning to keep it. Tonight I'm going to cover 2, 3, and 2, 4. Like I said, super straightforward. They're not very long, and they kind of go together. 2, 3 leads right into 2, 4. And then we'll do 2, 5 on Wednesday, and that's a pretty short section too. So I think what I'm going to do Wednesday, since I won't have anything else to do, is once I'm done with 2, 5, just like last time, I'm going to just still stay through the whole class, but maybe I'll just, once I'm done with 2, 5, I'll release you. And then if you guys had additional questions on anything from chapter 2, we'll just discuss them after we finish 2, 5 on Wednesday, because we will have some extra time. Unless you ask a ton of homework questions at the beginning of class, but that's kind of what I'm thinking for this week. I've been thinking about it a lot. Yeah, and we're in week 3, you guys. I know it just started, but it's going to be over before you know it. And then your asynchronous stuff will be 3, 1, and maybe a tiny bit of 3, 2, but definitely not 2 sections for that. Those are a little bit longer. Oh no, wait, I'm thinking 4, 1, 4, 2. Never mind. 3, 1. Yeah, it'd probably be 3, 1 and maybe a little bit of 3, 2 for your asynchronous work. We're on schedule. I can't believe it. I did promise Victoria that I would go over number 13 from the homework. If anyone else had questions they wanted to ask, think about what they are now so that we can go over them. Let me share my screen here.
Could you go for number 13 as well?
Yes. Didn't I just say 13? Did I say something else?
You did? I didn't hear. Sorry about that.
Oh, that's okay. Did I promise you a different one? Who said that? Was that Renee?
I didn't hear anything. I just heard you were going over homework questions and I really wanted to go over 13.
Oh, yeah. Yeah, so Victoria had asked about 13 and I didn't have time to get to it in the office hour. So I was going to do that one. But then if you did have another one, let me know what it is. I wrote down one variation of it. So someone else had, 2 other people had asked me a question about 13. Some of you had a 9, some of you had a 7. This one was a 6, but they're all going to work the same way. And the question was asking you to find f prime of c, and it was asking you to use the formula. limit as x approaches c of f of x minus f of c divided by x minus c. Yes. I'm going to really try to focus today. I laid down to take a nap this afternoon, and my son gets the phone at 4:30. So I was like barely asleep, and then he came in and was like, "Mom, there's a tornado warning." So he had picked up the spare phone, and nobody had touched it since yesterday. So he was reading like last night's tornado warning, and he was very upset about it. I'm like, okay, that doesn't apply, but thanks for waking me up. And then I never did get my nap, but that's okay. I got to close my eyes. This is what happens when you have kids, you guys. Just, I would say hold off as long as you can, but the older you get, the more tired you get. It's true. So I have no real advice for you on this. Not that anyone was asking. All right, so let's find this limit. Now, it's very important to notice that they didn't actually ask you to find the derivative at a specific number. The directions stated to find the derivative for any real number c. So what we're going to do here is we are going to take the limit as x approaches c, because we don't know what c is. It's just any general real number that we come up with. And we're going to take f of x minus f of c. And again, we don't have a value for c. So we're just going to evaluate f of c. Remember that f of c, you're just going to take your f of x, and wherever you see x, you're going to replace it with c. And then divide it by x minus c. Yeah, it seemed like I was getting the same homework questions over and over all weekend. So I started just copying and pasting my responses from people in WebAssign because I was just getting the same ones. And this was one of the ones I kept seeing. All right, so let's take the limit as x approaches c of 6 minus x squared minus 6 plus c squared divided by x minus c. If you have a question, let me know. Oh, there's something in the chat, which I just noticed. Oh, yes, I did check on the 5th of July. They say no. They say we have class, Morgan. So unless I hear otherwise, we have class. I could make it an asynchronous day, but you'll be coming off an asynchronous weekend. If you want, I can send out a survey and see what you guys want to do, because I don't know if you had like major plans. We don't have a test scheduled that day, do we? Look. No, but we do have a test scheduled for July 7th, which is the date after. So you have an asynchronous, 2 asynchronous days, and then you'd have a test. So might not be the best idea. Okay, so you have 6 minus 6, which goes to 0. And then you have negative x squared plus c squared divided by x plus c. Now, we are going to go ahead and factor this as a difference of 2 squares. In order to do that, rewrite, if you want, you can write the denominator as c plus x instead of x plus c. It doesn't matter. And then when you factor this, you're taking c plus x times c minus x divided by c plus x. Lots of factoring here because you keep getting these indeterminate forms, and in order to get rid of them, in most cases, you're going to have to factor and simplify. And then you're taking the limit as x approaches c of your remaining expression, which is c minus x. What happened? Oh, did I write? Oh, sorry. You know what I did at some point? I was wondering why would this go to 0? I somehow switched the denominator from x minus c to x plus c. Sorry. That should be a minus. If you were wondering, what is she doing? Definitely should be a minus. Okay, well, that changes a couple things here. Eraser pen. Okay, since I did that, I'm going to change my approach. Sorry, see how one little thing screws up my whole process? All right, so I had an x minus c in the denominator. I still have an x minus c in the denominator. Go ahead and factor out the negative if you want to think about it that way. And then you can rewrite this as x squared minus c squared, and then you'll still be in the same order. So that still leaves you with negative x squared plus c squared. You've just factored out the negative. And that's a trick that we use anytime we want to switch the order of subtraction, which I did in this case. Just, you could have also done that in the denominator. You could have pulled the negative out and then written it as c minus x instead of doing that in the numerator. You have some options. All right, so now we have negative, and now factor as x plus c times x minus c divided by x minus c. Cancel your x minus c's, and that leaves you with the limit of negative x plus c as x approaches c. Now, in this case, anywhere you see x, you're going to replace it with c. So you'll have negative and then c plus c, which is negative 2c. Were you asked to do anything else with this one? No. That's it. Other questions from the homework or questions on this one? Victoria, go ahead.
So I just wanted to know, so whenever we have a problem that has an x squared like this, and we're trying to find a derivative, we do, what is it called? The sub of square, whatever, I don't remember the term for it, but you know, like
Squares?
yeah.
Not every time. It just depends. I mean, I kind of jumped the gun here just because I didn't even bother showing you that this was indeterminate. But really, you have negative c squared plus c squared divided by c minus c. So this ends up giving you 0 over 0. Now, usually, if you don't get an indeterminate form, you don't have to factor anything. You can just take the limit as is. But in this case, you would have gotten an indeterminate form. So once you notice that, you're going to have to factor and cancel. So it's not anytime you see an x squared, it's just anytime you see that you have an indeterminate form.
Okay, that makes sense. Thank you.
You're welcome. Other questions here or elsewhere on your homework?
Could we look at 14?
14. Let's see. Okay, so this one says to differentiate, and then they want you to use the difference quotient. So the function is f of x equals 2x squared plus x plus 5. And just differentiate and determine the domain of f prime. They want you to use the form where h goes to 0 of f of x plus h minus f of x divided by h. So first we'll work on finding f of x plus h. Now, this is kind of a lot of work just because you have two different places in this function where you see the variable x. You have two different terms. So we'll have twice x plus h squared. Remember, when you square that, you have to multiply it out. And these parentheses here for the second term are non-essential, but I'm including them just so you can kind of see where I dropped in and evaluated this expression at x plus h. So there's 2x plus h squared plus x plus h plus 5. Then go through and simplify this. So x squared plus 2xh plus h squared. And then go through and multiply by 2. You might as well, just because there's not a whole lot more to do with this particular piece of the expression. And you end up with this quantity. I would probably hold off before you pop the limit on, but there's probably not a whole lot to do. You might as well just write it in case you decide to just go all the way. F of x plus h minus f of x. Now, remember, when you're subtracting off f of x, if f of x has more than one term, which in a lot of cases it does, you want to make sure you include parentheses around the entire expression so that this minus sign gets distributed. Divided by h. So simplify again by distributing that negative sign, and then we'll cancel out some additive inverses. And if you've done this correctly, you'll notice that all of the terms that came from your f of x function are going to be additive inverses with ones that you already have. So negative 2x squared, positive 2x squared. Negative x, positive 5, negative 5. And if you feel comfortable doing it, you can go ahead and cancel out some h's. But if I were you, I would factor them and then cancel them. I'm going to do that anyway because I'm the teacher. I don't want there to be a bunch of questions about where did this come from, where did that come from. So when I rewrite this, I notice that in the remaining terms, I have an h in every single one of them. So when I rewrite it, I go ahead and factor that h out, and then I just write the remaining numerator in its factored form. Don't forget that when you factor h out of h, you still have 1. And now you can see that you can cancel out these common factors of h. You'll take the limit as h approaches 0 of 4x plus 2h plus 1. And remember, I know sometimes it's hard for students to remember that you are not going to be evaluating your entire expression at 0. You're only sending h off to 0. So the x, you're treating like a constant at this point. It's not going anywhere. So you'll have 4x plus 2 times 0, which is 0, and then plus 1. This is f prime of x. And the other thing you were asked for was the domain of f prime of x. It's a polynomial. Its domain is all real numbers. You don't have any variables in the denominator. You don't have any radicals. Nothing like that. Anything else bugging you guys from the homework? Or questions on this one? All right, then let's talk about derivative rules for polynomial functions. Now, I love doing this section because if you've never had calc before, you'll do the material from 2-3 and be like, seriously, everything we did in 2.1, I could have done like 10 minutes faster. Yeah. And then if you did have Calc 1 before, you're like, oh, why do I have to do these derivatives using limits? This is so ridiculous. I already know that there are formulas for this. Yes. So this derivative that we just found that took me forever to find, not forever. Okay, it took like probably 7 minutes. We used the whole difference quotient. We evaluated the function. If we would have messed up one little thing, our derivative would have been wrong. There was a lot going on there. And this was a little bit more of a straightforward function. I mean, some of these were a little bit crazier as far as having radicals that were in the denominator. I'm thinking about one in particular that someone asked me about on the homework. I don't remember which one it was now. I have all these notes from just me answering WebAssign questions. I don't remember. I don't see it now. But anyway, the whole point is, by the end of today, you're going to be able to find f prime of x in like 10 seconds without having to do this. And then you might be wondering, like, why do we have to do this? Well, technically, I am going to ask you on your test to use the limit process to find f prime, and then to also find f prime at a number, and maybe to give me the equation for the tangent and normal lines. So you do have to know how to do this, but in 2.3, 2.4, 2.5, you're going to learn rules for doing these things that take a lot less time. So this is an essential skill. It's important to know where this comes from, but the rules in 2.3 are going to make your life a lot easier. Which makes me happy because I know it makes you guys happy. And anytime you guys are happy, I'm thrilled. Sometimes it's hard to make a calc class happy. So we're gonna try for it today. 2.3, the derivative of a polynomial function. And the derivative of y equals e to the x. Okay, so we talked a little bit about notation in 2.1 and 2.2. You're going to be using pretty much the same notation here, but you might be introduced to new notation along the way. We have a couple different ways of denoting derivatives, so I want to make sure we are aware. So we know about f prime of x. So that's the derivative of f with respect to x. I don't think we used y prime. But y prime is the same thing as saying f prime of x. We know that f of x is synonymous with y as long as y represents a function in x. So f prime of x and y prime of x both will denote a derivative of y with respect to x. Another notation that we're going to use is the Leibniz notation. It's dy over dx. We usually don't say dy over dx. We usually just say dy dx. So we're going to use these interchangeably. Depending on what we're doing, you might see this more often. Later on, there are sections where I'm explicitly going to be using this all the time. But most of the time, if I just ask you to find a derivative, you can just note it by y prime or f prime of x. Something you might see not very often is this capital D f of x. There's no operator between them. It's called operator notation, oddly enough. We don't use it a lot. This will be more similar to stuff you might see down the road in Calc 3. But. Oh, and by the way, as far as the Leibniz notation, I forgot I had an additional note on this. If you have dy dx, the derivative of y with respect to x, you could also see that written as d dx of y. I mean, it's the same thing. If you take a fraction and you multiply it by an integer, you can just move that integer into the numerator. It also is just d dx of f of x. So what this means is the derivative of y with respect to x. So the derivative of y with respect to x. X being the variable with which you're taking that derivative. And if you're wondering, like, why does it matter? If, I mean, obviously we know it's with respect to x. Well, it's not always going to be. Even this week, we're going to be looking at functions that aren't called f of x. Maybe they'll be called s of t or v of t. A lot of times we deal with functions that are with respect to time, and we denote them with t instead of x. So you might see something like that. So it is important to note the variable with which you're taking the derivative. And then in the next chapter, when we talk about implicit differentiation, we'll talk about actually taking a derivative of an equation that is not written explicitly in terms of x. And you're going to have to kind of tag that on. So that'll be in chapter 3, which is something to look forward to. But this is the notation that you'll be seeing in 2.3 and actually throughout chapters 2, 3, and 4. And then we'll sort of move away from this a little bit in chapter 5. All right, so I'm going to give you a bunch of theorems here. I'm going to try to make them brief. You know, I was explaining to a student, what was it, like 2 semesters ago, they were like, you know, all these theorems, it's just a lot, and just all this notation. Can you just say it in words that are easier? Well, first of all, this book is pretty straightforward, so the theorems are not that complicated. The reason I actually go through the theorems is because when I was a student at ECC, my teachers didn't a lot of times, some of them did, but a lot of them didn't. They kind of told us everything in plain words. And even though that was awesome for me as a student, when I got to U of I and started taking math classes towards my engineering degree, I was so lost because I didn't know what any of the notation meant. And the worst part about that was it wasn't that I didn't know how to do the math, it was that I didn't understand what the question was asking because I couldn't read the notation. So I know that we love to just see things, you know, in examples, and we're like, why do we have to write down these theorems? A lot of times I feel like part of my job as your calc teacher is to prepare you for what you're going to see after this class. Otherwise, I'm not really doing my job to the fullest extent. And having had that experience as a student, I just would hate for my students to get to their university and be like, whoa, theorem, corollary, what's going on here? That's why. That's why I tend to write all these out so that you get used to seeing things written in more general notation. Derivative of a constant. But how about we abbreviate if you don't want to do all the writing? Derivative of a constant function. If f is the constant function, f of x equals a, then f prime of x equals 0. Or you might want to think of this as d dx of a equals 0. So it's a constant function. That means that f of x equals some number. And remember that if we're talking about a function that is equal to some number, we're looking at a function that's graph is represented by a horizontal line. And with each one of these theorems, I'm going to give you an example, and then we're going to put all these theorems together and talk about finding derivatives for polynomials in general. So this might look something like, oh, here, maybe I'll number these. Maybe that'll be helpful. F of x equals 4. So that would be an example of a constant function. Then f prime of x would be equal to 0. Sometimes students get used to thinking about constant functions the way they did with limits. The limit of a constant is whatever that constant is. It's not the same thing with derivatives. With derivatives, you're taking the derivative of your constant and getting 0 every time. And if you remember how a derivative of a graph is related to the graph of the original function, then hopefully it will make sense why your derivative is 0. I mean, if you think about the fact that your constant function, f of x equals 4, if this is your function, remember that the derivative of a function will have negative values when your function is decreasing, and it will have positive y values when it's increasing. And when it's constant, that you're going to have an x-intercept there. Well, this function's constant all the time. It's never increasing, never decreasing. So your derivative will always be the graph that is always an x-intercept all the time. That's kind of why that works the way it does. Your function's not increasing, not decreasing. So your derivative is always going to just be that x-intercept all the time. So there's that. We also have the derivative of f of x equals x, that identity function. If f of x equals x, then f prime of x, which is the derivative of x with respect to x, is equal to 1. You're also going to note with these polynomials, I think I mentioned it in your asynchronous video, but you probably noticed along the way, if I didn't mention it, I think I did, that for a polynomial function, your derivative is always going to be 1 degree less. So if you have an x, then your derivative is 1 degree less. So x to the first, x to the 0. In this case, you already had x to the 0, so now you have nothing. So that's kind of how that works. And you're going to see that pop up again and again. So this is a basic rule. We're going to tag this onto your simple power rule. Now, this book drives me crazy because I really like the book, but it's a slow build here. If you've had Calc 1 before, you're going to continually ask me, like, when are we going to do this? When are we going to do this? I'm telling you, the way they develop these power rules in this book is so slow. Okay, so I will give you the simple power rule. The derivative of the power function. And by the way, you're going to use this derivative rule all the time. This is extremely important. I mean, all of these you're going to use like all the time. The derivative of the power function, y equals x to the nth power, where n is greater than or equal to 1, we must make sure that that variable is not negative. Otherwise, you end up, you need to make sure your x1 is not negative. Otherwise, you would end up with a variable in the denominator, which is not a simple power function anymore. And it's an integer, because you don't want to have any radicals. Okay, y prime, which is the derivative with respect to x, of x to the n. Make sure we're all ready, because I'm going to give you the simple power rule, which will change your life. It will. Life-changing. Your calculus life. All right, here's how it goes. You're going to take the exponent off of x, and you're going to pull it out in front of the function. You're going to rewrite your variable x, and then you're going to decrease the power by 1. You're going to use this every day, many times a day. And I'm going to give you an example of this. Example 2, f of x is x to the 8th power. F prime of x, well, here's what you're going to do. You're going to take the exponent out front. So move the 8 in front of the x, rewrite the x, and decrease the power by 1. Now, I don't expect to see you write 8 minus 1. You're just going to take 8 and subtract 1 and write 7. But I am showing you this for the first time ever, so I'm including that. You must simplify it so that you actually perform the subtraction. F prime of x is 8x to the 7th power. But can you imagine, I was just thinking about, what if you had seen a problem like this in 2.2 where you were asked to find the derivative and you had to actually take f of x plus h, and you had to take x plus h to the 8th power? It'd be like a total nightmare. This took what, like 2 seconds? your whole life is just so much better right now. Okay. You guys have questions so far? Or are we doing okay? Doing good? All right. All right. We have a constant multiple rule that kind of is going to go along with these previous two theorems. Constant multiple rule. If f is differentiable and k is a constant, then f of x equals k times f of x is also differentiable. So you have some function and it can be written as a constant multiple of another function. And f prime of x equals k times f prime of x, or we could say d dx of kf of x is k times d dx of f of x. So just like with limits, you can take the constant multiple and pull it out front, and you can work on the actual function of x and then multiply it by the constant multiple. You don't have to move the constant multiple, but you can. So it's just saying that this is an option to you. And a lot of times you will use that option. It'll make your life easier. And we'll use that constant multiple rule now. This would be example 3. So our first function will be f of x equals 3x to the 7th. And you're being asked to find f prime. So f prime of x, you can just leave the constant multiple in front and then just take the derivative of x to the 7th. So you'll have 7 that gets moved out front, and then x to the 7 minus 1 is 6. So this one just uses that simple power rule with a constant multiple. And then, of course, simplify this to 21x to the 6th power. And we'll do another one with the fractional coefficient. F of x is negative 1/3 x to the 4th power. So in this case, we're taking our simple power rule, or simple power function, x to the nth power, and multiplying it by some constant k. So to find f prime, you can leave the constant multiple right where it is, and then multiply by, bring the power out front, rewrite your variable, and subtract 1 from the exponent. And remember to simplify, you got to rewrite this as negative 4/3 x cubed. Any questions? You guys aren't too shy about asking questions. I just want to make sure that I'm giving you time to ask them. Don't be shy. Okay, we also have a summer difference rule, just like we did with limits. And you'll find that you use this one quite a bit. If f and g are differentiable, and if capital F, this is your function, is the sum or difference of two functions, f of x plus or minus g of x, then your function's differentiable. So it's saying if the two components of your sum or difference are differentiable, then your main function is also differentiable. And if that's the case, then capital F prime of x is equal to little f prime plus or minus little g prime. And if you want to see that in different notation, d dx of f of x is equal to d dx of f of x plus or minus d dx of g of x. Sorry. Okay, so those were the rules that I had for differentiating polynomials. Now I'm going to give you 5 examples where we're combining polynomials in some different ways. And we'll take their derivatives. Before I do that, are there any questions here? I'm actually remembering to look at the chat now, but nothing is happening, which is fine. Okay, so example 4, differentiate polynomials. The first one will be f of x equals 1 plus x to the 7th power. Now we're going to use that sum or difference rule here, and actually in all of these examples, we're going to be using it. So we're going to use the constant rule for the first term, and we'll use the simple power rule for the second term. Now remember that the derivative of a constant is not the constant itself, it's 0. So the derivative of 1 is 0. Obviously, you don't have to write this. I'm writing it because I'm the teacher, but I'm going to simplify it so that we don't have it there anymore. For the simple power rule, bring your exponent down. Then you have x to the 7 minus 1 power is the 6th power. And then your derivative, f prime of x, is just 7x to the 6th. So we actually use 3 rules there. We use the sum or difference rule, which actually is the sum rule in our case, the constant rule, and the simple power rule. B, f of x is 3x squared plus 4/3 x cubed. Now, when you take derivatives, you like for everything to be written in separate terms. What I don't want you to do is say, oh, well, maybe I could just factor it and write this as x squared times 3 plus 4/3 x, and then just take the derivative. I mean, I don't know why you would do that, but don't do that. And I'm going to show you why in 2.4. We actually are going to have rules for if you're taking the derivative of a product or a quotient. You can't just take them separately. Like with limits, you could take the limit of a product was the product of the limits. That's not the same with derivatives. You can't just take the derivative of one factor and multiply it by the derivative of the other. So you want to have this expanded so that you have a series of terms. Remember, we can only use the rules that I've given you so far. And I haven't given you really that many rules. You know that you have a sum or difference. You have the x rule, the simple power rule, and the constant rule. That's it. But in this case, we have two functions where we're going to use the constant multiple rule along with that simple power rule. So we're going to leave the constant multiple out front, bring down the exponent, and then take x to the, and then in this term's case, 2 minus 1th power. So decrease your exponent by 1. Then we'll use the sum rule. And the constant multiple rule says we're going to leave the constant multiple where it is. Bring your exponent out front. Then take x to the, decrease the exponent by 1 power. I'm going to simplify this, but are there any questions here? So we have 6x plus, here your 3's are going to cancel, and that leaves you with 4x squared. Now, leave your answer like this. It's not a big deal to me if you want to write your answer in factored form. And there are some times when we are going to want to take our derivative and factor it. But if all I'm doing is asking you for the derivative, just leave it. Don't do more work than you have to. It's done. Stick a fork in it. Don't worry about doing anything else crazy to it. The last thing you want to do is factor it and get all fancy and factor it wrong. That'll be terrible. Okay, C. F of x is 1/4 times the quantity x to the 6th minus 5x cubed plus 2x. Okay, now remember I was just explaining to you that we don't have a rule that allows us to take the derivative of each factor and multiply them together. If you're going to take the derivative here, you're going to have to rewrite this so that you have separate terms, and then we can use the sum and difference rules. So you must, in a lot of cases, rewrite the original function before you can even take the derivative. So this is one of those cases where you must rewrite f of x before you differentiate. So I'm going to have to go ahead and multiply in the 1/4. And I'm going to show you another example in a minute where we're going to have to rewrite the function also in order to take its derivative. So we haven't done any derivatives yet. All I've done at this point is just rewrite f of x so that we get rid of this product. I don't have a product rule yet for you. I will in 2.4, but this form requires the product rule. In 2.4. And honestly, even when you learn the product rule, which you will very soon, you wouldn't use that on something like this. You would always distribute the 1/4. It's a lot easier than using the product rule for something like this. Okay, let's take the derivative then. 1/4 times, bring the exponent down. So multiply by 6, and then times x to the 5th power. Minus 5/4, bring the exponent down, reduce the exponent by 1. Now we have the x rule. I know we haven't actually used it yet. It's somewhere. It's like 2 pages ago. There it is. The derivative of f of x equals x. If f of x equals x, then f prime of x equals 1. We're going to use that here with the constant multiple rule. So the derivative of x is 1, and the constant multiple stays. And then we'll just simplify. 6 divided by 4 simplifies to 3/2, and then x to the 5th minus 15/4 x squared plus 1/2. There is your derivative simplified. I guess you could have taken the derivative of this function and then multiplied that whole derivative by 1/4. You could have done that also. But I don't know. I think it's easier. If you're going to have to distribute it anyway, I'd rather just see it distributed right away. It's up to you. D. I'm going to ask you, I'm going to switch the notation up a little bit. D dx of, in the numerator, 3x to the 6th minus 4x squared, and in the denominator, 7. So instead of saying f of x equals, I'm asking you for the derivative with respect to x of this function. So that's assumed to be your function f. Okay, now again, I cannot just take the derivative of the numerator and divide it by the derivative of the denominator. I wouldn't even want to, because the derivative of a constant is 0 and I can't divide by 0. But I can't do it anyway because I haven't given you a quotient rule yet. So you have a couple options. You could take the 7 out front as 1/7, or you could just split it up into each term of the fraction. Personally, knowing what I know about students, I think that's what you would do. So that's what I'm going to do. So I'm just going to split up this fraction using the common denominator. And I know we've done that a couple of times in the last few weeks. So the 7 is going to go to each fraction. So I have 3x to the 6th over 7. And if you want, write this so that you have it in the form of using the simple power rule. And then minus 4/7 x squared. So if you want, just instead of having that x to the 6th in the numerator, just kind of leave it right there being multiplied, and then it looks more like a constant multiple. Sometimes it's all just about the way it looks. Questions there before we take the derivative? Okay, now the notation is different here. So I'm asking you for the derivative, and I'm saying the derivative of this function equals, so all you need to do is just tell me what it's equal to. So once you take the derivative, you can drop the d dx. I'm going to take 3/7 times 6, x to the 5th, minus 4/7 times 2, x. Now it's technically x to the 1st. You don't have to write the 1 in the exponent. It's unnecessary. And then simplify. You'll have 18/7 x to the 5th minus 8/7 x. And then I have one more for example 4, and that's E. And again, mostly I'm just showing you this because I wanted to switch up the notation a little bit. I'm looking for dz dc if z equals 2c cubed plus 1. So what that really means is I'm looking for dc of 2c cubed plus 1. So in place of the z, I'm dropping in the expression z equals 2c cubed plus 1. Are there any questions on the notation before I take the derivative? All right, so once I take the derivative, I can drop the ddc because this is saying the derivative of blah, and you're saying, okay, well, that equals constant multiple, bring the power down, reduce the power by 1, and the derivative of a constant is 0. So it's 6c squared. And that is dzdc if you want to write it like that. Okay. Any questions there?
I have a question.
Sure.
So, you did 2c cubed plus 1,
Yes.
and then the 1 turned into 0.
Mhm.
How did it turn to 0?
So
Okay.
since 1's a constant, the derivative of a constant is 0. The limit of a constant is the constant itself. The derivative of a constant was that first rule way back when. So if f is a constant function, then f prime of x is 0. So if, if f of x is 4, then f prime is 0. So we just use the sum or difference rule with that rule.
Thank you.
You're welcome. Any other questions there? You get more paper. I feel like I'm going to run out while you think of your questions. All right, then I'm going to give you the derivative of the exponential function y equals e to the x. It's probably the easiest derivative you're ever going to see in your whole life. Theorem. If y equals e to the x, then y prime, which is dy dx, equals e to the x. The derivative of e to the x is e to the x. That's it. That's all there is to it. I don't think I'm zoomed in any more than normal, but I moved my camera. I record your asynchronous lectures downstairs, and every time I move it back, things are different. So we'll use that. Example 5, f of x is 6 e to the x plus 3x cubed. Okay, so f prime of x, we're going to use the constant multiple rule with the exponential e to the x rule. You're just going to take that constant multiple and multiply it by the derivative of e to the x, and the derivative of e to the x is e to the x. And then take 3 times 3 x squared using the constant multiple rule with the simple power rule. And you'll have 6 e to the x plus 9 x squared. Now, I hope that I'm going to catch it when it pops up on your homework, but your book has an issue where it, instead of giving you e to the x, your book will say e to the x, but WebAssign will give you like e to the 2x. Not the same thing. That's technically not something I'm going to teach you until I teach you the chain rule in chapter 3. So I'm going to try to catch that. If you catch it on the homework where you're asked to find the derivative of e to the 2x or the 7x, just give me a heads up and I'll remove it, because I can't see it in the book and I can't see every iteration when I assign it. I don't know why they do that. They did that with the last book I used too. It wasn't WebAssign though. They would just like drop it in randomly in the homework assignments. Terrible. Okay. I'm going to give you a function and we're going to answer a series of questions on this so that we can kind of tie it into what we did in 2.1 and 2.2, mostly in 2.1. Example 6. For f of x equals 3x minus e to the x. And we're going to look at this at 0, -1. The first thing we're going to do in A, I'm going to give you 4 parts here, is find the slope of the tangent line. Now, you actually would not have seen a function like this in 2.1 with an exponential in it, but you would have had to have gone through that whole process of either using the difference quotient or taking f of the limit as x approaches c of f of x minus f of c divided by x minus c. This time we're just going to use derivative rules. So when you're being asked to find the slope of the tangent line, we're going to find the derivative and then look at the derivative at this point that I gave you, 0, -1. So instead of going through this long process to find f prime of 0, we're going to find f prime of x and then just let x be 0 and evaluate it. So remember, the slope is the derivative. So we're going to just use our derivative rules. The derivative of x is 1. The constant multiple means you multiply it by 3. The difference rule allows us to subtract. And the derivative of e to the x is e to the x. So that's our derivative. So that's an equation for the slope at any given point on this curve. But we're talking about what's happening at the point 0, -1. Morgan, go ahead. What's your question?
Can you just explain again how you got 3 from 3x?
Yeah, so the derivative of x, going back to that x rule, is 1. Where was it? Here. There it is. Whoop. Yes, if f of x equals x, then f prime of x is 1. But since it's 3x and not just 1x, then you're combining that with the constant multiple rule. So you're taking the constant multiple and multiplying it by 1 to get 3. And if you like the simple power rule better than using that x rule, that's kind of the way that I did it as a student, was I used the simple power rule. Side note, if you had f of x equals x, you could still consider this using the simple power rule, but technically x is x to the first, right? So you could bring the exponent down, keep your variable, and subtract 1 from the exponent. And then you could just write this as x to the 0. Well, any real number to the 0 power is 1. That's why the derivative of x is 1, because you can use this simple power rule to get it. Does that help?
Yeah. That makes more sense. The side note helped a lot.
Cool. I'll put a little cloud around it. Yeah, I think you'll get used to just using that, and you'll just over time get comfortable with knowing that if f of x is x, its derivative is 1. And then using that in conjunction with the constant multiple rule. But you can always go back to this anytime you forget or you need to verify. So we found f prime of x. In our case, I gave you the point 0, -1. So we're focusing on what's happening at x equals 0. So remember the x coordinate is the first one listed in your ordered pair. So we're going to take our f prime of x, and we're just going to, everywhere we see x, we're going to replace it with 0. And any real number to the 0 power is 1. So that means that f prime of 0 is 2, which is your slope. All right, questions on part A? You might be guessing where part B is going to go. I'm going to ask you for the equation of the tangent line. So I asked you first for the slope of the tangent line. Now I'll ask you to find the equation of the tangent line. And I'll just remind you, the point is at 0, -1. Okay, so remember we're taking y minus f of c. You know, I'll just write the formula down for you because it's been a few days maybe since you looked at it. Y minus f of c equals f prime of c times x minus c. In point slope form, you'd write y minus y sub 1 is m times x minus x sub 1. If you remember that from algebra and you feel more comfortable with writing it that way, then write it that way. Doesn't matter to me. It does not matter to me if you use this particular notation. I don't. I use this one because I also teach a lot of algebra. Okay, so y minus f of c, well, I gave that to you. This point is c f of c, if you will recall. So y minus -1, be careful there with your double negatives, is equal to m. Well, we found that in part A. We found that the slope was 2 times x minus, and then c in our case is 0. We'll have y plus 1 equals 2x. And whenever you write the equation of a line, I like for it to be in the slope-intercept form, which is y equals mx plus b. So you'll have y equals 2x minus 1. Now, I did not double check this, and for some reason I didn't even think about it till just now. WebAssign is very liberal with what it accepts. And it might have accepted something like this when you were going through your homework. I don't know, I didn't double check. But on your test, I'm going to specify that I want your equation written in slope-intercept form. And this is, here, I'll write it down. Slope-intercept form is y equals mx plus b. All it means is solve for y. Basically, I don't really care about exactly what's happening on the right-hand side. I mean, obviously, I want it simplified, but solve for y. So when I ask you on your test, write your equation in slope-intercept form, this is what I'm asking for, y equals mx plus b. For part C, we're going to find the equation for the normal line. And again, we're still looking at CF of C as 0, -1. That has not changed. Remember that to find the slope of the normal line, you're looking for the perpendicular slope. So everything else is going to stay the same in this equation. You're just replacing f prime of c with -1 over f prime of c. It's just the opposite reciprocal of your slope. So you'll have y minus -1 equals -1/2 times x minus 0. And y plus 1 is -1/2 x. Subtract 1 from both sides, and you'll get y equals -1/2 x minus 1. And if you want, you can even graph these. You can graph the original function f of x, which is 3x minus e to the x. Graph the tangent line, graph the normal line, and you can see what that looks like on the graph. You don't have to. I'll just show it to you now because, oh, part D is graph f the tangent line and the normal line. Of course it is. I'll just write it on the next page. Part D. Graph f, the tangent line, and the normal line at our point 0, -1. So your function was 3x minus e to the x. Now, if you're not used to graphing exponentials, your e to the x is going to be second natural log, and that's going to pull up an e. Now, if you have an older calculator, it's going to say e, and then it's going to give you that caret symbol and a parenthesis. And you're just going to enter an x in there. If you have a newer calculator, it's going to give you the template. Let me quit this for a minute so I can show you what it would look like. Well, actually, I don't even know how to make it appear old style. No, never mind. It'll be like e, and then it'll give you caret. I put in caret, and it won't even let me write caret. I can't do it. I wish I still had my old calculator because it would be really helpful with students who have older calculators to display that. But it's e, caret, parenthesis, x, close parenthesis. Same idea. Your tangent line is y equals 2x minus 1. If you want to graph the graph first, just to get a good idea of where it is, you can do that. I like to go to Zoom 6 before I graph, just to make sure I'm not in some crazy Zoom. If I'm in a crazy Zoom, sometimes it takes forever to graph the function. All right, so the tangent line is 2x minus 1. And if you want to see these separately, we'll graph that one first. Oh, there it is. Oh, I love this one. Notice the point we're looking at is this y-intercept here at 0, -1. And you can see that your line 2x minus 1 is tangent at that point. It just barely, it starts to approach your graph. It hits this point at 0, -1, and then it continues on its path. It's just a straight line. It's tangent. It hits your graph in this one spot and one spot only. And then we'll do the normal line, which we're expecting to look like this, which might be a little bit skewed on your calculator because of your viewing window, which we can always square off if you'd like. We can square it. Your normal line is -1/2 x minus 1. And graph. There it is. And again, like I was saying, it doesn't really look perpendicular. So what you can do is you can go to Zoom Square, which is number 5. And it will change your axes so that you have this 1-to-1 ratio on your screen. And it should look perpendicular once you do that. There you go. It's better. Okay, you don't actually have to graph it here. On WebAssign, you're going to be doing a multiple choice for something like this if you see it. And on a test, I wouldn't actually force you to graph these. It's not really something I would test you on. I just really think it's important to illustrate the concept so that you can see how these lines are related to your graph at that point. Okay, questions on example 6? I want to do one more multi-part example, really kind of examining what's happening with these derivatives. And this will be my last example for 2.3. Example 7. And we're going to be focusing on 2e to the x minus x plus 1. The first thing I want to look at, and I don't think I have asked you this. You might have seen one of these on your homework on 2122, but I cannot remember if they had it or not. Find the points, if any, at which the graph has a horizontal tangent line. Now, I mentioned it briefly today. I mentioned it briefly over your asynchronous lecture. But thinking about how the graph relates to the graph of the derivative, when your graph f is increasing, the y values for your derivative are going to be positive. When your graph f is decreasing, the y values for its derivative graph are going to be negative. But when your graph is constant, you're going to be sitting there at an x-intercept. And when your graph is constant, if you think about what's happening, now this is not necessarily the case for this graph, but anytime you have a situation where you're looking at a curve and you hit a peak or a valley, you come to this place where all of a sudden your derivatives become 0 for your tangent lines. So imagine you've got these tangent lines running through. As you approach this point, all of a sudden they level out once you get to the top. And then once you start to get over this hump at the top of your hill, maybe you are looking at a point down here, for instance. Well, now your tangent lines are starting to decrease again. So your slopes start to go down. What we're looking for here are points on our graph such that the graph has a horizontal tangent line. And points where that occurs are going to have slopes that are 0. Remember that a slope of 0 means that you have a horizontal line. So in algebra, we're talking about the difference between horizontal and vertical lines. Well, vertical lines have undefined slope. Horizontal lines have a slope of 0. So note, horizontal lines have 0 slope. So if you're trying to find points at which the graph has a horizontal tangent line, then we need to find places. So we're going to find where f prime of x is equal to 0. Now, we're just kind of lightly touching on this today, but this is going to be a huge concept moving into chapter 4. You're going to be taking a bunch of derivatives and just setting them equal to 0 every single day in chapter 4, because we're going to really be focusing on where our tangent lines have a slope of 0, and that's going to be important because it's going to allow us to find a maximum value on a graph and a minimum value on the graph. Because if I know that my tangent line has a slope of 0, then it must be the case that I've hit some sort of a peak or a valley. That's why this is going to be a really important concept to us moving forward. Today, we're going to touch on it. We're going to use it. It's not going to be a huge emphasis, but it will be. So we're trying to just get your feet wet today. To find places where the slope is equal to 0, you're going to take the derivative, and we're going to set it equal to 0. I gave you f of x is 2e to the x minus x plus 1. So we're going to take f prime. Now, I mentioned before that you should not be seeing anything where you have anything other than e to the x on your homework. If it's e to the 2x, e to the 3x, e to the kx, anything, we should not be seeing that at this point. That's something I'm going to go over in the next chapter. WebAssign should not have included those. I forgot to complain last semester. I don't even know if they would have removed them. If you see that, that's a problem. But if you have a constant multiple in front of e to the x, that's totally fine because that doesn't actually affect the derivative. The derivative of e to the x is still e to the x, and you can still use that constant multiple rule to find the derivative. So the derivative of 2e to the x is 2e to the x. And then we talked a couple times today about the fact that the derivative of x is 1. So use that difference rule and write your derivative as 2e to the x minus 1. Remember, you're just decreasing that exponent by 1. Now you have no x's. The derivative of a constant is 0. You don't need to write it. You should be getting pretty comfortable with that. So here's your derivative, f prime, 2e to the x minus 1. Questions there? So we're trying to take this derivative and set it equal to 0 to find values of x where the slope is 0. So we're going to solve this equation. I'm looking for 2e to the x minus 1 equals 0. So we're going to set f prime of x equal to 0 and solve for x. Sorry, I always run out of space over here because this thing is blocking my hand. Okay. Solve for x, you're going to use your algebra rules. In this case, we'll add 1 on both sides of the equation. And then we'll divide both sides by 2 because we're going to need to isolate x. So isolate e to the x first. And then if you don't remember how to solve an exponential equation, if you want to get the x out of the exponent, take a natural log on both sides. This is something you should have learned how to do in college algebra. Or algebra 2, whenever you had it. Remember that the natural log of e is 1, but this allows you to take the exponent out. The natural log of e to the x is just x. So we would say that x equals the natural log of a half. Now, again, you can use rules here and split up that natural log and write it a bunch of different ways. I'm just going to leave mine as natural log a half. Now, on the test, I found it odd. Maybe you were nervous. There was a set of 2 examples where even though I stated for the whole test that I wanted your answers exact, for those examples, one answer was, I think, 1 plus e to the 1 plus 5e. And I even said at the beginning of that particular exercise, leave answers exact, like don't approximate or something. And still a lot of you approximated. Now, if you wrote the exact answer and gave me the approximation, well, that's fine, no big deal. But if you didn't simplify the exact answer and you just approximated, then you lost some points. I want exact answers. This is exact. An approximation of this would be if you went to your calculator and you plugged in natural log 1/2, you would get approximately negative 0.693147. Now, that's just for purposes of maybe we want to find this on the graph later and we want to know where to look. As far as finding all of our equations, we should be using this exact form. This is a decimal that does not terminate. Notice it keeps going and going and going and going. It's going to keep going because E is an irrational number. However, where was I going with this? Keeps going. Oh, yes. If I just cut it off here at 6 decimal places, even though that's close, I don't want to keep using this truncated version in my work because then my final answer is going to have these tolerance issues where I rounded the decimal and now my next answer is also rounded because I've based it off of a rounded answer. So I want to be careful to keep using my exact value until I get to the end. But for part A, I asked you find points at which the graph has a horizontal tangent line. We're expecting that to occur at x equals natural log 1/2. So you should see on your graph, if you were to graph this function, which we could do if you wanted to, 2 e to the x minus x plus 1. If you were to look at the graph at approximately negative 0.7-ish, you should see that you have a peak or a valley there. I think I'm still in Zoom Square, but that's okay. And there you see it. Right here is approximately at like negative 0.7-ish, and that's where you're seeing this graph dip to the bottom, and then it starts to go up again. So it makes sense that you would be seeing this horizontal tangent line right about there. You can even trace it. I don't know how close you can trace it, but if you hit the trace button, well, actually you could. You guys know how to find the minimum on a graph? If you're not sure, I'll show you how right now. And you can verify this. You go to calculate, which is second trace. And the option for minimum is 3. And it's going to ask you for a left bound and a right bound. So you can move to the left of where you think that minimum is, just whatever you have to do to make sure you're to the left of it. And you hit enter. And then it's going to ask you for a right bound. And you're going to scroll over to the right of that minimum, somewhere to the right of it, just as long as you know for sure you're to the right of it. And you're going to hit enter. And then it's going to say guess. And then you will say yes, enter. And it's going to tell you that the minimum occurs at approximately x equals 0.693148. Did we round wrong? It's possible. But this is giving you an approximation for where that minimum point is. That's good because that matches what you showed here for a place where you would have a horizontal tangent line, which would occur at a maximum or minimum value on the graph in most cases. Okay, I'm going to put this away because it's not really essential, but any quick questions on that? Wonderful. Part B. Find an equation for the horizontal tangent line. Okay, now in order to find the equation for the horizontal tangent line, you are going to need C f of c. We're looking for an equation where this occurs. Well, we're looking at the x value, ln 1/2. So we're looking at ln 1/2, and then we need f of ln 1/2. Because this is all occurring at this particular point. Now, normally I'd give you CF of C. In this case, you found C. You found the point where you would expect to see that horizontal tangent line, and you just need to find the corresponding function value. So f of ln 1/2, you're going to go back to your function, this one, 2e to the x minus x plus 1. Maybe I'll rewrite that so you can see it down here. So if we have f of x is 2e to the x minus x plus 1, then it must be the case that f of ln 1/2 is 2e to the ln 1/2 minus ln 1/2 plus 1. Now don't freak out, because in the same way that ln of e to the x is x, e to the ln of 1/2 is a half. They're inverses. So we have twice 1/2 minus ln 1/2 plus 1. Which is 2 minus the natural log of a half. Okay, so to find the equation of the horizontal tangent line, I needed a point. I also need a slope. In order to use point slope form, you need a point and you need a slope. So I have now a point, which I can fill in, because now I have it. ln 1/2, and then the function value f of ln 1/2 is 2 minus ln 1/2. So this is our point. And we already know the slope, because we know that the slope of a horizontal tangent line is 0. We know that. We found it. That's how we found this to begin with. We took the slope and we set it equal to 0. So yes, we're going to use that here. Okay, before I continue, does anybody have a question? All right. If you really want, you could use the whole formula, but really a horizontal line is just going to be the line that goes through f of c, wherever that is. So if you just want to say y equals f of c, that's plenty. If you feel like, I don't know if I would have come up with that on my own, that's fine. Use the formula. Y minus f of c equals f prime of c times x minus c. I should block this off here. And then you can just plug it in and you will come up with that same result. So y minus, and don't forget your parentheses, 2 minus ln 1/2 is equal to f prime of c, which is 0 because it's a horizontal slope. And then it does not even matter what else is occurring. What was our x value? Oh yeah, ln 1/2, because it's being multiplied by 0 anyway. So all you need to do is solve for y by adding this quantity to both sides. Y equals 2 minus ln 1/2, which is, notice, the same quantity that you had over here. But we're going to graph this, and then you're going to see that it's actually the y coordinate of that minimum that you found on your graph. Someone's asking me a question. Victoria, go ahead.
Yeah, I just wanted to clarify, to like add the 2 minus ln 1/2 to both sides, you would have to distribute that negative. Did you just flip the signs in order to get the 2 minus ln 1/2?
I just took the whole quantity. Since it was already in parentheses, I just said, let's add this chunk to both sides. And because it's in parentheses already, I can just take it as one unit. But
okay.
you could have distributed it, and that would have been fine. And if you would have done that, this would have been a plus. And then when you subtracted it from both sides, it would have become a minus again.
Okay, gotcha. All right, thank you.
Yeah. So if you want, just do that off to the side and verify that that is the case. But yeah, I just took it as one quantity. I'm glad you asked. Other questions there on part B? Okay. Excellent. Oh yeah, we're gonna graph the horizontal tangent line in a minute. I first want to do part C. Solve f prime of x is greater than 0. So we already found the derivative and we set it equal to 0, and we did that in part A. I'm going to remind you of that right now, if I can scroll up there. In part A, we took the derivative and we set it equal to 0. So now we're going to take the derivative and set it to be greater than 0. And we're going to basically get a very similar result. But if we set it to be greater than 0, then I'm taking f prime of x, which remember we said was 2e to the x minus 1. And I'm going to take this 2e to the x minus 1 and force it to be positive by setting it greater than 0. And then we'll say 2e to the x is greater than 1, and e to the x is greater than 1/2. And same process, when we're trying to get that x out of the exponent, take a natural log on both sides. And you'll get x equals, I made it an equal sign when it's a greater than sign. X is greater than ln 1/2. So this seems like, okay, why did we even do this at all? We pretty much already did this, except with an equal sign, and that's correct. But I want to put all this together with the graph in a minute. Do something similar, but this time solve f prime of x is less than 0. What we're looking for are places where your derivative is less than 0. Why would I care about that? Why would I care about when the derivative is less than 0? Well, you should be thinking that if your derivative is less than 0, that means your derivative y values are less than 0. And if the y values of your derivative are less than 0, it means that your original function is decreasing. So what I'm really asking you to do here in parts C and D is find places on F where your graph is increasing or decreasing. So we're going to put all this together in the graph in just a minute. But same idea. Take your derivative, set it to be less than 0, and you'll get e to the x is less than 1/2. And then ln e to the x is less than ln 1/2. So that means x is less than ln 1/2. Something's missing there. So exact same thing, except that time with a less than sign. Now, to formalize this, this means f, not f prime, f of x should be decreasing for x less than ln 1/2, because the derivative values were less than 0. And this means that f of x should be increasing for x greater than ln 1/2. Verify your result graphically. So we're going to say graph F and the horizontal tangent line. We'll do that now. So f of x, we said, was 2e to the x minus x plus 1. And the horizontal tangent line was y equals, what was it? 2 minus ln 1/2. But we'll graph both of these. The first function, f of x, should already be in your graphing calculator. So there's your function. Your horizontal tangent line is that constant, so there's no x in it because it's a constant function. So you're looking for this horizontal line, x minus ln 1/2. I'm sorry, 2 minus ln 1/2. Got x on the brain here. Now, what we should see is that you've got this horizontal tangent line running through the bottom of your curve. If you don't, then something has gone wrong. Oh, but nothing went wrong. We did a great job. There's your point, x equals ln 1/2, which was about negative 0.7. And then you have the corresponding y value at that point where you have this horizontal tangent line running through. Back to our conclusion for part D. We were talking about when your derivative was negative. Well, the derivative of this function, we could graph it. Should we do that? Yes. The derivative was 2e to the x minus 1. Let's get rid of your horizontal tangent line for a minute. Let's graph the derivative. 2e to the x minus 1. And we can actually see how the graph of f is related to its derivative. Okay, ready? I love this stuff. You guys, I'm so excited right now. I love this. Okay, there's your function. All right. Here's the derivative. Okay. Remember how these graphs are related. When your original function is decreasing, the values of your derivative, the y values of your derivative are negative. That means that they lie underneath the x-axis. Well, look at how they start to come up here. Now, when your derivative has an x-intercept, that's where your function reaches its minimum value here. Then it starts to increase. And as soon as you hit this x-intercept, now your derivative has positive y values. Well, that means that at that x value, your function starts to increase. I really want to plant these seeds because this is all going to be used so often in chapter 4. And I want us to get really familiar with this idea of how this graph is related to its derivative and what the derivative means in terms of your actual function. Okay. Oh, you guys, I have terrible news. I am not going to get to start 2-4 tonight, and that means I don't think we can actually do your test on Thursday. Are you really disappointed? Okay. Yeah, I only have 5 minutes left, and it's really not enough time to even do anything. Okay. We're going to have to just proceed normally. And obviously, I can't cover 2 sections on Wednesday and give you a test Thursday. The nice thing is that when I start chapter 3, you're going to be using all of that stuff in chapter 2. So it's not like you're learning totally new stuff. All right, I'm gonna have to think about this. Because you also have that asynchronous work. Okay, that's fine. I'll have to think about this. I think we'll just do asynchronous 3-1 and you'll just have to take your test Monday. And the nice thing is you'll have Tuesday. So I'll probably have the asynchronous work not be due until that Wednesday. So if you wanted to do it before the test, you could, but you didn't have to. I think that's what I'll do. Because I don't want you to feel like, oh, I'm trying to study for this test and I have all this asynchronous work to do. Like, I'll make it available. It will relate back to this. It won't be on your test. But then at least you'll take the test Monday and you'll have Tuesday off if you want to finish it. What do we think about that? Something was in the chat. Was it a snide comment? Let's see. Okay. Okay. And that gives everybody time because I was kind of surprised by how many questions I got on 2-1-2-2. So hopefully this gives everybody a chance to catch up on that. So let's plan for that. I'm going to write it down formally. We're going to move test 2 to Monday. And that's a week from today, even though it's going to be the 28th. Okay. So sorry if you had major plans scheduled for the 28th. That's a bummer. Yeah, but such is life. Okay, so let's do that. And then on Wednesday, we'll do 2-4 and probably start 2-5. And then Thursday, we'll finish 2-5 and then kind of see where we end up. I was actually shocked that we were on schedule anyway. So this is not like a big major deal. That's all. I'm going to put up some homework for 2-3. And you guys have a wonderful evening. Let me know if you have questions, okay?
So we don't have like a quiz on Thursday?
Oh yeah, that means you'd have a quiz Thursday. Yeah, that's a great question. I'll have to remind you of that on Wednesday.
Okay.
Because technically you wouldn't have a test, so you would have a quiz on Thursday, which really should help you prepare for your test. 21, 22, 23, 24. Yeah. But you wouldn't have a quiz Monday because you'd have a test. Yeah, and thank you for asking.
Yeah,
I
thank
didn't
you.
think about that. Okay. Any other questions?
Yeah, can you go over question 3 for the quiz that we had today?
Question 3. I have a feeling question 3 was like that question that Burfin asked me right before the quiz. Burfin, you lucked out.
I was
Yeah,
so
that's how I
happy about
get
that.
it too. Oh, I'm sorry.
Let's see. I think I have it written down, but actually I can just get it from here. Let's see. Yeah, I'll do this real quick. Let me get it. Gosh, this paper is thick. One sheet of paper. All right, it was of x equals 2x squared plus 1, negative 1 minus 4x. X is less than negative 1, x is greater than or equal. Let me see here. There we go. Quiz question 3. Okay. So you can graph this automatically and see if it's discontinuous. And if there's a discontinuity, then you would know right away that the derivative wouldn't exist at that point. But it could be that the function is continuous and the derivative still doesn't exist at that point, which is why I like to go through this looking at the one-sided limits. So I would say take the limit as x approaches negative 1 from the left, Now, as you approach -1 from the left, you're looking at values of x that are less than -1. So that means you're on the function 2x squared plus 1. So you're taking the limit as x approaches c of f of x minus f of c, all divided by x minus c. And if f of x equals 2x squared plus 1, then f of -1 is going to be 2 plus 1, which is 3. So you'll have f of x minus f of c, which is going to be minus 3, divided by x minus -1. And that would be your setup for your left-hand limit. Questions there?
No, I'm following so far.
Okay. All right, so simplify your limit. So you'd have 2x squared minus 2 divided by x plus 1. Right off the bat, this should be crying out to you that it would like to be turned into a difference of 2 squares. So factor out the 2, and then you might see that a little bit more clearly. So you'll have twice x plus 1, x minus 1, divided by x plus 1, and then you can cancel out those common factors of x plus 1. And now you can take the limit as twice -1 minus 1. 2 times -2 is -4. Now, your goal here is to either show that the left and right hand limits are the same, or you can show that they're not the same. If they are the same, then your function's differentiable at that point, and the value of f prime would be -4. If they're not the same, you would say that the derivative does not exist at that point. So we'll take the limit as x approaches -1 from the right. Now, when that happens, we're looking at this function because we're looking at values to the right of x or of -1, and that's -1 minus 4x. So we're taking f of x minus f of c. Well, if f of x is -1 minus 4x, then f of -1 is -1 plus 4, which is +3. So we'll take that and we'll subtract it off, because remember, we're subtracting off the value of f of c. And then we're taking x minus c. And then we'll simplify again and see what we come up with. So this one will give us -4x minus 4 divided by x plus 1. And then when you factor out the -4, you'll get common factors of x plus 1. The limit of a constant is the constant itself. And because -4 equals -4, it must be the case that f prime of -1 equals -4, and the derivative exists at that point. So your answer would have been yes, f prime of c equals -4.
Okay, thank you a lot. Have a
You're
good day.
welcome. You too.
Thank you.
You're welcome. Good night.